be the part dedicated to the Stardust samples analysis, so the Stardust NASA mission. And also, I will speak later about Rosetta and Comet Interceptor. Okay, why we somehow associate comets, which are bodies so small and so, I mean, even not so beautiful when they are not close to the sun somehow, why they are so interesting. Okay, I already said it a bit about it, because they actually remained in the as they formed. So they have hints and footprints of something which was there during the formation of the solar system. And then we saw that they contain water and they contain organic molecule, and somehow they provide energies in some situations. So actually it's quite old, the theory that looks at the comet like something, like objects that can have contributed to the process of having life on Earth. But it's not the theory, I mean, I will not speak about that, because that they brought already something biological. I'm saying that they contribute with the ingredient that it's useful to start biological form. So it's kind of having this passage from here to here, instead of something which is on Earth and only on Earth, that it's providing life from ingredients that have been always on Earth and available. And this is also connected a bit with what I told you before about water on Earth, that maybe it was brought after its formation. And the fact that actually already in this molecular cloud observation of amino acid or of let's say important ingredients for life, they have been observed by radio observation from ground, and since the solar system, you know that it's coming from these molecular clouds. You already learned it, and I showed you briefly at the very beginning. It means that these ingredients somehow were present in the protoplanetary nebula, and if we go and study comets that somehow remained as when they formed, maybe we can learn something about this theory. In fact, what I say here, why comets, they're witness of a distant past. And when I say distant, I say both in time but also in space, because they are probably formed with the building blocks that were coming from the molecular cloud. So this means that they, of course, the comets formed from far from the sun and remained kind of unchanged. They contain water, they contain organic molecules, and so they can tell us something on how the solar system forms, and perhaps they suggest something, they could suggest something also on how life originated on Earth. And let's say that this theory, it's coming also from a timeline. If you put here, you see, let's say, Earth formation at 4.5 billion years ago. Then you see here the 3.9 billion, about billion years ago. It was a moment that it was called big bombardment. Somebody do think it was, somebody doesn't, but as I said, models, theories are all welcome because they help to understand really how nature is made. And the fact that it's so close, the date where it's supposed to have to occur this type of bombardment, which was of course due to the fact that the solar system was forming, and as I told you, for instance, a mass like Jupiter's one didn't allow to form a planet in the asteroid belt. There was also the fact that these small bodies, they didn't have their own stability, equilibrium, gravitational equilibrium, so they were traveling in the interplanetary medium, and somehow they were attracted from bigger bodies like planets, for instance. And the date of the most ancient rock containing trace of biological life, it's dated like 3.8 billion years. So somehow you can think of this period with the big bombardment, a period very harsh. It was, I mean, it shouldn't be so pleasant to be on Earth at that time, but as well a delicate in our mind process, like the starting of life. It's strange to be so close to such a period in which the situation was not in equilibrium and calm, and so scientists started to think that there was kind of a connection between the big bombardment that could have brought something that was useful to for the life to begin. So just having a very synthetic summary of what we need, and so which would be the ingredient that could have been important for the starting of life, we can summarize it really basically like having water, organic molecules that of course are prebiotic, and energy. So the energy in comets, it's just due to impacts, because we know that they are bodies that are they do not they are not active, so they do not have energy, but when they impact they really release big amount of energies. So this is the reason why comets have been really I mean, with respect to their mass, they've been really very well studied with respect to mission dedicated to these minor bodies. Normally, till before Rosetta, all the cometary mission, they were in a configuration of a flyby. Flyby, I think you all know, it means just the passage, very fast passage of a spacecraft close to the nucleus of a comet. And in fact, also Stardust was one of these missions. It flew by comet 81 P Wilt 2. It was launched in 1997. It arrived on 2004 on the comet, and then it brought back samples to Earth. You see that it arrived. I'll show you a video afterwards. It arrived, it passed at about 300 kilometers from the nucleus, and opened this capsule here and exposed these blue things here, which is a panel made of aerogel, which it's a very strange material. And exposing it, it collected particle, and then it closed again the probes, and the spacecraft came back to Earth. It released this capsule, and with the double opening of parachutes, it landed softly on the Utah desert. So this is these are the characteristics of the mission. It was, even if it was very peculiar, it was the first time that was done something like this, a sample return from a known object, even if now they are, I mean, I told you about Hayabusa, Osiris-Rex, but in this case it was the very first time it happened. And something very special, it's also this part here. You see the sample analysts were about 200. This is because you know that for space missions, you have kind of a closed period to use the data within the scientists that really participated to the development of the mission. So for 6 months, only people that are involved in the mission, this for all the missions, only people in the within the team of the mission can use data. This means that all the news that are coming out from for the measurement of that mission are let's say are closed only for those who really participated to the mission. In this case, what NASA did was to make a call, and since this 6 months it was very short, and analyzing the material was not trivial. You know that if some of you does experiment in a lab, one knows how difficult it is sometimes to deal with instrument that doesn't work, and then you have to prepare the sample, then it doesn't work. So all these things, doing them in such a small period, it was very hard. So the risk was that the results were, I mean, very few in that period, and then the samples would have been spread to the laboratories that were requesting. In fact, also now, I mean, if you are interested in analyzing these samples, just make a proposal to NASA and they will give you the samples. But in that case, they wanted to be sure that that everything that could have been done in that close period was possible. So this is why the NASA made a call all over the world for people who were working on extraterrestrial material, on laboratory analysis of materials, for instance, meteorites or interplanetary dust particles. You know that NASA has also this program to collect in the upper stratosphere interplanetary dust particles that are actually residues of comets and asteroids. They are what you call normally the falling stars that you see in the sky. They come inside the atmosphere and they just burn up. But sometimes if you go, especially if you go up, and I will, if I have time, I will speak you also about an experiment that we are doing in our team for collecting this dust. But in any case, the call was open for people that already had some of this experience, and they selected. So we, in Italy, I prepared a proposal as a PI with other colleagues to participate to this close period of the mission, and incredibly, I couldn't believe it, but I was selected. My proposal was selected. So I had, I mean, it was kind of beautiful working in that period, in that community, with, even if it was very tough, because everything had to be done in very short times and night and day. I mean, holidays or not, you really were focused on that. But during that period, the PI of the mission organized some workshop, and going in this workshop, it was just beautiful, because every presentation, every discussion, it was new, because those it was like having a puzzle, and at every of these workshop that were, of course, open only to the 200 scientists that NASA selected. It was like having a puzzle, and every time you put another piece close to the other. So it was very, very, beautiful. And to participate to that. Okay, the comet is actually periodic comet, so it's a comet that already were passing close to the sun, so somehow modified, not like the one that we hope to observe with Comet Interceptor. It was, you see that by the time of the Stardust encounter made only, in any case, only 5 trips around the sun. So it was chosen just to have a comet relatively young. And I think here there is the, okay, I will not show you the whole video because it's too long.
Stardust, bringing cosmic history
I
to
think
Earth.
there is not the volume of the video, but
Comets are believed to be
yes,
the most
it's
ancient objects in our solar system. Made of ice, dust, and carbon, these celestial beacons are thought to hold secrets to the early formation of the planets and the sun.
So you see the comet is coming from far from the sun. It's just a rock, actually. It
When
doesn't
far
have
from the sun,
any
a comet's
tail or
nucleus is
nothing.
cold and its material frozen solid.
And then as soon as it's closer
As the
to
comet
the sun,
travels towards the sun,
the
the ice
activity
begins
start.
to warm and the materials begin to evaporate, forming an atmosphere called a coma,
you see
creating an
this
enormous tail
process
which
of
fluoresces in
sublimation and
sunlight.
activity of the comet is still not understood. I mean, it's not trivial to understand why the sublimation would, why there
One
is
of these
such a
cosmic
pressure
interlopers,
of
Comet
the
Bilt 2,
sublimating
was the
gases
destination
that
for
can
Stardust.
bring up this
NASA's Stardust mission
refractory
is managed by the Jet
material.
Propulsion
And for
Laboratory
Rosetta,
in
we
partnership
also
with
observed
Lockheed
kind
Martin
of
and the University of Washington.
meters
The ambitious goal of this
of
mission
block
is an
of
historic
material
journey that
from
will
the
bring back to
surface
Earth the
going
first
up, so you
samples
can
of a
imagine
comet.
the pressure that should be there. So we are still studying this aspect, which is not at all
This
clear.
850-pound
There are
spacecraft
different
was launched on
models, of
February
course,
7,
that they do
1999
work
aboard
till
Boeing Delta
a
II
certain
rocket
point, but
from
still
NASA's
is to
Kennedy
be
Space Center
developed.
at Cape
So
Canaveral,
you see
Florida.
that the probe was brought up, of course, with a rocket, and then it went. You
After
see
5
these
years
two
and 2.1 billion
brownish
miles of travel,
things here and here.
Stardust
Of
encountered
course,
Bilt
they were
2
kind of
on January 7, 2004.
shields to protect the solar panel from impact,
As
not
Stardust
only
neared the
during
comet,
the
spacecraft
moment
deployed its
of
collector
the
grid to capture
of
particles
the
comet.
encounter, but also
This
in
tennis
the
racket-looking device
interplanetary
contains
media,
over
you
100
can have
ice cube-sized
objects that could
compartments
have
filled with the world's
destroyed
finest
the
known
solar
material,
panel.
a
Here is the
silicon-based
aerogel
substance called aerogel.
shroud. You see,
These
this
comet
is the
particles, moving
material.
at 6
It's
times the
aluminium,
speed of a
the
bullet, collided
the
with the
structure,
aerogel.
and then you have
With a
these
heavier
blocks of
substance, the
aerogel,
comet
which is a
particles would
very,
vaporize,
very porous
but the light
material
aerogel
that
surfed
could
and
have
slowed down the particles, capturing for
decelerated
scientists
the
these
particle
microscopic
and
clues to the
stopped them,
formation of the
not
solar
passing
system.
through, of course,
But
but
catching the
without
particles required
modifying
more than
the
aerogel.
material too
The
much.
spacecraft
You have
had
to
do its
think that
part to
the
soften the blow
speed
capture
of the
by lowering its
encounter,
speed at
so
time
the
of
speed
encounter.
of the impact was at 6
Still,
kilometers per
Stardust was
second.
traveling
So it's a
13,000
lot of
miles per hour
energy
when it passed
when
through Bilt 2's coma,
particles
coming
are
within
impacting on a
149
material.
miles
For
of the
instance,
comet's
those
nucleus.
particles that were impacting on the aluminum frames, they were completely destroyed.
such
They
close
formed
range, the
craters,
possibility
and the particle was
colliding
completely
with
melted.
destroying
It was
spacecraft
interesting also to study that residues, but to have the particle let's say, more or less not modified. It was important to use a very low density material, which is this aerogel. So you see the the panel, it's put back in the probe. The probe is closed, and then the spacecraft is coming back around Earth, and the probe it's detached from the spacecraft, and then it was so it's deployed, and then it was coming through the atmosphere. This is a technology that only NASA has till now. It's not trivial. Of course, you can imagine something that it's passing through the atmosphere. If the falling stars, they are quite small when they do this big light. You can have these big lights also for particles like millimeters inside. But this kind of probe, it was very important to make a shroud with a material that was really resisting those very high temperature. And then the use of a double parachute assured that, because of course it's a falling object, you know the gravity on Earth, you can imagine the acceleration and the velocity with which it could have reached the Earth's surface. But with this double opening of a parachute, the probe, the little probe, could land safely. And then with helicopters from the NASA agency, they went there and picked up the capsule and brought it in a clean room to see if the samples were there. And so this is the aerogel I was talking about, and it's very nice to work in different space mission, because you always learn something, not only from a scientific point of view, but also from a technological point of view. In fact, what I anticipate here now is that this material, we knew it when we were studying as scientists, the material in which the cometary particle were trapped, but we learned a lot about this material. And now that we are designing an instrument which will fly on comet interceptor, we are building the instrument using this material. So it was never used as we are doing it now, but since we learned something about it, then we decided to use it. ESA was not so happy about it because, as I was saying to some of you before, it's difficult to convince the agency to use something which was not proven to be working. But in this case, since OnStarDA was used, since we also use it to put it in the International Space Station to collect interplanetary dust particles, and we demonstrated with experiments in lab that it could work, they accept our idea. And it's very convenient. In this case, we will not use it. I don't want to make confusion. We are not using it to collect particles, because Comet Interceptor will not bring back samples on Earth. It will just perform a flyby. But since our instrument is an instrument which is coming from the heritage of JADA, which is the instrument I was responsible for on Rosetta, it will be exposed to the dust, because it will measure the momentum of each particles, and probably the speed of the encounter will reach kind of 60 or 70 kilometers per second. You can imagine this hypervelocity impact, which energy they can have. So we have the sensible surface, and underneath the electronics, and we don't want the electronic to be destroyed. So we put a layer of aerogel in between the electronic and the sensing plate, and we demonstrated that this dust shield does work. And so the aerogel, which is very convenient material, because you know that sending spacecraft in space is very expensive when you when your instrument is very heavy, because the more the mass, the more difficult is everything. And so if you put light material that in any case work, they at the end were very happy, because with this layer of aerogel we didn't increase the mass of the instrument. So this is just to say that it's very nice to learn from the experience. And it's very important for the agency not to lose the knowledge that people gain in a space mission. You know, it was very sad after Rosetta, that was a very long space mission, especially for the for the younger people, to having had all these experience and then lose it, this heritage. It was really a pity. So luckily, even if Comet Interceptor is not comparable to Rosetta as a space mission, at least it's a cometary mission. So the young people that were working in Rosetta, they will follow the space mission, Comet Interceptor mission, till the end. I think myself, I will be, I think, kind of retired, but I'm happy that people younger than me that work with me on JADA, Rosetta, they will be still there and they will apply what they learn. So cometary sample arrived back to Earth. This is a real image of the capsule entering the atmosphere. And this is also a nice movie that it recalled. This is the capsule on the Utah desert, and you see that the collection of the capsule was kind of an extraterrestrial body found on Earth, because in fact it's something that, I mean, was really in a strange place for the first time and brought back to Earth something that was coming from a big distance, both in time and in space. So the capsule was brought in a clean room in Houston to be opened without possible contamination. And then, even at the first glance, Mike Zaleski and Don Brownlee, they could, Mike Zaleski it was the responsible for the curation of the samples, and Don Brownlee was the PI of the mission. They already could see by naked eyes these tracks that the particles made in this aerogel. Then the aerogel blocks were extracted from the aluminum structure, and these tracks were studied. You see, the particle was entering from the upper side, and they arrived in such a high speed, as I said, 6 kilometers per second, that the volatile part exploded and made this type of track shape. But the particle, what was called the terminal particle, so the more compact and less volatile, more refractory part of the particle, arrived till the end of the track. The particles were extracted, so these are the some examples of tracks and of particles found at the terminal particle found at the end of the tracks. You see here you have these terminal particles, but also the particles were present in the tiny small pieces of the particle, because as I said, it's not that they collected really intact this particle, because the speed was so high, the energy was so high that the particles were some kind of changed. But the main aim of the mission was not to study the volatile part, but more the refractory part. Otherwise, it would have been much more complicated, the mission. And then, as I said, I'm very have been very, very happy to participate to this phase of the mission, because it was this workshop were something that really I will never forget. I mean, every time was something new, was unpublished, and was just to learn every time we had a workshop within the team. Just to show you some results, for instance, we obtained at the first time 7 grain extracted from this part of the track. We were very interested in having particles, even if they were fragments, but in the volatile part. And in fact, we asked for this particle extracted from this area, and we could analyze them and found there the organic molecules that we were expecting to be there. But as I said, it was quite. I mean, even if it was kind of foreseen, was the first time that you had in your lab material that was not only extraterrestrial, but you really knew the parent body of it. So you directly connected the results you had in the lab to the source of the body from which this particle was coming from. Then, of course, everything was very new, and in fact, for instance, a new mineral that it doesn't exist on Earth was found, and it was called brownlite. Okay, it's coming from Brownlee, which is the surname of the PI of the mission, but it was kind of a new material that new mineral that it doesn't. It has not been observed at least till now on Earth. To get the sample, we have been studying an ad hoc sample holder. You know, if you work in laboratory, that sometimes the preparation of the sample, it's much more complicated than the measurement, because you want to, for instance, for these small particles, it's very difficult, the manipulation, because they are small and because you don't want to contaminate them. So since our aim and our proposal to NASA, when we were selected as part of the preliminary examination team, we stated that we would have been able to apply multiple analytical technique to each sample. And in fact, we applied scanning electron microscopy and EDX to know morphology and composition, but also micro-infrared and micro-Raman spectroscopy. So before we got the samples, we made a lot of exercise in laboratory, building up different sample holder that was designed ad hoc on purpose to be able to just take it with the sample on it and then stick it into the scanning electron microscope and into the micro-infrared and to the micro-Raman. So the same substrate, it's not trivial, because with different analytical technique, you need different characteristic of the substrate. But at the end, we could design a substrate that was, that performed very well with respect to what we intended to do. And also, very important, it was kind of be sure that we could have identified the particle where it was deposited by NASA. So the design of the substrate allowed us to identify the particle. There was a mixing up at the very first phase, not on our side. Let's say I don't want to, but I can tell you something more in case you are curious about this. But I will not do it now because I'm recorded. Okay, so about sample preparation, as I said, it's very important to really to study the sample order. And after the first configuration, in the second phase, we asked for some terminal particles, so those particles that reached the end of the track. And we decided to use another type of holder, which was allowing us also to smash the particle and to analyze better the distribution of different components that was present, that were present in the particle. So we have chosen these particles, for instance, and then we put it in a diamond cell. We press it, and the particle from this shape, it arrived at this shape, and then again the TP3, terminal particle 3 particle, it was enlarged, and everything was more smooth and easier to be analyzed. Of course, in this case, we had to state our intention of modifying the particle, because you have to know that in this sample return mission, you want to have a part of the sample that it's, as you take it from space, you just put it in a clean room, in a kind of database that they have in Houston. They have all the extraterrestrial material like put there to wait for future analytical techniques to be developed. So always available in case something new occur, and it's kind of a reference. So nothing has been done on those samples that are still as they were collected. Then there is the part which is distributed to the preliminary examination team, so to very small group of scientists, 200 scientists all over the world. And in that case, we had to state if we were applying destructive analytical techniques or if we had the intention of modify them. So they would have checked for the steps we were supposed to do, and they allow or not to be this operation to be performed. In this case, we of course stated that we would have pressed, and if they understand that the balance of knowing something else with respect to modify a particle is okay, then they allow you. And so this is what we have done with these particles, and in this case we could have understand the distribution of the different elements in the particle, and in both particles. And what I would like to focus on is, if you see, this is the 10 micron size. So these are really very small. Okay, now they are enlarged because we press them, but if you see the homogeneity of the such small particles, you already understand something on how comets are made of. So it was very nice to participate. Again, when you get experience, it's always nice. Participating to Rosetta, having this background, it was really very nice, because everybody was at the beginning in Rosetta, in the Rosetta community, in this SWT, they were speaking about olivine grains of 200 microns. They were not observed. Okay, in stardust, such big, homogeneous, big, because of course 200 microns with respect to these of the same mineral, they have not been observed in stardust. So either you think that every comet is made on its own way, structure, or you think that they are almost similar one to the other, at least some family comets, families, they have something in common. And I wouldn't see the reason why these minor bodies are so different one to the other. But in any case, what I saw with stardust samples, it was not that you had these very homogeneous particles. Okay, this is what it was found in the material of the comet, the presence of glycine. But since this, as I said, it was not one of the main aim of the mission, because the protocols involved, they were not designed to study the volatile component, the organic component. So this is a finding. It was published, but it was also very much discussed, let's say, because of course the contamination issue, it's especially in a material like aerogel, which is very porous, very absorbing. Okay, but I just report what it's published. So to have a summary of what Stardust found, one very important finding is that that actually induced scientists to modify also planetary formation and solar system formation models, was that some minerals, even if very small in size, were found, and these minerals can form only at high temperature. This means that the building block of this comet somehow is coming from, let's say, from temperature that you can have only between the Sun and Mercury. So very high temperature. This means that even if the comets were formed very far away from the Sun, somehow some of the material had to be transferred somehow at the edge of the planetary nebula, either on the plane or out of the plane. Of course, this was not really considered before in these models, but the fact that the particles are showing this type of mineral, it's really, it's telling something for sure. Then what was observed, that cometary particles are weakly constructed mixture of subgrain of various size, different composition. As an example, I'm showing you one of the grains that were the particles that were analyzed, and you see this is a 8 micron in size, and you see here the composition, the unhomogeneity of a single particle such small. You have 3 different components. So, and more or less all the samples that were observed were in this condition. It's what I was talking you about before. Also our grains, our particles that we observe, they are made up of different grains, different components. in a very on a very small scale. So then, of course, the presence of oxygen and nitrogen, high oxygen nitrogen contents, the presence of Ca2H2 and CH3, that this ratio, it's also providing information on how much the material, the carbonaceous material, is primordial. There is a classification that you can do by Raman spectroscopy, and so to studying the structure of this organic component, and to that it's being compared with other terrestrial material to understand how really primordial is this component. The fact that probably this comet, like other periodic with short period comet that's coming close to the sun often, they let's say that there is a slight difference between pristine and primordial. This is the terminology which is always confusing, I think, between different communities. But it seems that comets do not seem so pristine as we used to consider, let's say, the comets, so reservoir or something that has been always far from the sun, stayed there, formed the comet, and so they are really the result of something which is never changed with respect to the very first times during the solar system formation. But since also minerals that formed at high temperature, so something coming from inside went outside to form these bodies, we rather say that these comets are not pristine but primordial. So let's say saying that primordial, it's representing the time of solar system formation. Okay, so after Stardust, Rosetta came. Stardust, as I said, it was the first time that cometary sample arrived on Earth, but it was quite a fast mission, and but very focused on an objective, which was, yes, the spacecraft had some instrument that were performing remote sensing observation, in situ observation, but the main part was to collect particle and bring back to Earth. While Rosetta, it's a much more complicated mission. I just tell you, just to give you an idea, that I was working on JADA, which is the instrument I was responsible for at the scientific phase of the mission, but I was working on this instrument when I was a PhD student. So you can imagine, and since I'm not a genius that I just went very fast in my career, so we had a lot of time between when the mission was designed, that it was in late 80s. So you can imagine also the technology that was on board Rosetta. And then the moment in which then it was launched in 2004, and the scientific results were reached from 2014 2016, the scientific measurement. So it's really a lot of time. And then there are a lot of first time for Rosetta, first time, and we will see that. So the name, as you were asking for, the Rosetta Stone discovered in 1799 made us understand the hieroglyphics. And also the objective of the Rosetta mission was to understand the language, to decipher the language of comets. So studying a comet really well in depth to really use something more general of these minor bodies. Rosetta was still is, but it's on the comet. But a spacecraft that carried a lander, a small lander. You see the dimension of Rosetta. So Rosetta, it's quite a small spacecraft. It has a lander, but I have to go back. It's a lander. The lander is the dimension of I always say a washing machine, just to get an idea of the dimension. But the solar panel are really special. Since the propulsion at ESA cannot be nuclear, so we have to go everywhere with solar panel. In this case, Rosetta was supposed to go so far from the sun that the solar panel had to be really big extension, and to give the energy to the spacecraft, but actually not enough for the world trip. And in fact, from a certain period, for about 30 months, it was hibernated. Everything on the spacecraft was switched off, and otherwise the energy was not enough to reach the comet. And here is the spacecraft at ESTEC, ESA, in Norwich, where the instrument where the spacecraft was assembled, and also the instrument. And here is the instrument for which I was working with my PhD, but also as a responsible of the instrument since 2010. And then here you see the lander Philae, which was then deployed and let it landing on the comet surface. And then here it's OSIRIS, which is the camera that provide beautiful images of this unknown world. Okay, this is just to be a bit proud of Italy. Allow me to do it just very fast. So there was JADA, which I was responsible for. And then there was also another instrument, which is Virtis, that it was responsibility of Italy as well. And then the part of OSIRIS, the camera, but also on the lander, there was a driller that was under the responsibility of an Italian institution. Okay, this is I put some videos that were like very also painful somehow, because for the community who worked in the mission, because you can imagine that when you spend so many years after something, then every moment which is a bit critical, then you really live without breath. And this was the moment when the Rosetta was hibernated, and the spacecraft, everything was switched off. Only a clock was on, and at a certain date, at a certain time, it should have given the signal to send a signal to Earth. And so it was the moment when we were waiting for this signal, but if this signal was not arriving, then everything was lost. But luckily, even with some delay, it arrived. So everybody was very, very happy. You see Andrea Comazzo, he was the responsible for the Rosetta operation. He was the one that when we arrived, you see 6 August 2014, there was the arrival of Rosetta close to this body, which was very, very strange. You can imagine that while it's easy to orbit around a spherical object, in this case it's a very small object, and also this gravity field, it's very strange. So Andrea was saying that till that point, Rosetta was traveling like a Ferrari in a highway, and at that point, Rosetta was traveling like a bus in Naples. So, and who knows Naples? Understand well. He knew Naples because he was there to for a period of his life. You see that when this is the landing on the surface, and unfortunately, okay, the place that was chosen, that was selected, was actually the one that was at the end where the landing arrived. But it's also true that unfortunately, as I said, the gravity field is very weak. This means that the lander that was arriving there, it was just a ballistic release, so it had to go with a certain trajectory without any thruster. Only some thruster were on the upside. Okay, this is just to comment, it's the very end of Rosetta, so you see all these faces without the volume, but all these very sad faces were justified because it was the very end of the mission. And you can imagine also the Rosetta community, how was involved also, I mean, at this stage, also, I mean, with our feelings, because after 2 years of working together, meeting often, and having new results, and working, and maybe don't understand the data, but then understand them, especially when we put them together among instruments. But at the end, you don't have any more that toy, let's say, and it was really very, very strange. But now I forgot what I was telling you. Never mind. Let's go on. Okay, this is again to be on my side. This is just to give you an idea on how small is a comet. Okay, Rome is not such a big city. Actually, it's big if you consider all the, but if you consider only the center of Rome, then you get an impression on how the comet was small. The final descent. In this case, it was also very strange. Rosetta is a spacecraft, a space mission, because normally when you have a space mission to a certain target, what you do is to study that target and then select another target to go and to be studied as a second step. For instance, Giotto, it flew by Comet Halley, but then it went also on Comet Griggs-Kjellerup as to continue to use the spacecraft again. For Rosetta, it was very strange situation because we had all these very harsh and tough period and phases. And the spacecraft, as I said, it was a technology, quite an old technology that we weren't so sure even to do the scientific phase that they would have worked also after the hibernation, because you saw that signal was, we were waiting for it from the spacecraft. But then every team of every instrument went to Darmstadt, and we went there when we had to have the signal from JADA. So we knew that we were sending up a signal, and we had to wait about 20 minutes, because you know that the speed of light it's high but finite. So we had, because of the distance, we had to wait, and then we had to wait the signal back from JADA. And I mean, it was kind of a feeling waiting for it, and you know, if it wouldn't come back, then everything was ended. But at the end it worked, and all the instrument worked. So this was really successful. But at the end, even if it was not foreseen, Rosetta was decided to be directed on the nucleus of comet Griggs-Keller, Churyumov-Gerasimenko, because it was such a long time that was around the interplanetary medium. It faced so many difficult phases, and the technology was so old that it was a bit. And then it studied such in depth a comet that foreseeing a flyby to another comet, it was kind of. So the SWT, the scientific working team, together with the engineers, decided to make the spacecraft landing on the comet. But it, of course, the spacecraft was not designed to do that, but at least the instruments were on till the very end of the arrival on the surface, so we could measure areas that were not foreseen to be observed. And so also in that case it was like gathering important measurements and important results. So this is the final descent that was decided by the Rosetta team in large. And after some orbiting of the comet, some ellipsoidal orbiting to learn also how to fly so close to the comet, the final orbit was directed towards the nucleus. And also in this case it was decided where to make this spacecraft landing. And in fact, the foreseen place was very. It was the goal was reached, and the idea was going close to one of these very strange structures that are not really craters, because they are kind of cylindric holes that come si dice pozzi health. Okay, never mind. In any case, holes quite just to we wanted to know something more about those structures, so we went with the spacecraft close to one of them successfully. But then, of course, at few meters from the surface, the spacecraft had to be switched off, because it's not foreseen from ESA to leave spacecraft without any control. So some of the people working in Rosetta, they would like to let Rosetta be switched on in case something would have survived. Of course, it was not designed for that, so probably it's smashed on the surface, but just in case. But the rules from ESA doesn't foresee this, so it was completely switched off at few meters before impact. Am I late? Okay. So these are some images of these new words, because it's something when I still remember my feelings of looking a new word for the first time, and it was quite nice. Then these are the images that tell us something that look from very close the raising of the activity of the comet, because Rosetta followed this comet when approaching perihelion and then going back outbound from perihelion. So the onset and of the activity was observed. This a bit of number just to give you an idea of the body that we observed. What it's very interesting, it's the density of the body. You see it's very low density, high porosity, 70-80% of porosity, and this is also what it gave hints on revising a bit also the formation of this type of body. From the albedo and from other measurements, the presence of organic material was very, very. This material was very abundant, and let's say that with respect to Stardust, the two missions are a bit complementary, because Stardust couldn't observe so well the volatile component, but more the minerals present in the samples. And Rosetta could observe a lot the organic and volatile components, also ice on the surface. The only instrument that gave information about the composition of the particles present in the nuclei is Cosima, which has had the opportunity to collect the particle in situ. Of course, no material went back to Earth, returned to Earth. That return, it's a bit strange word actually, because it never been on Earth before. So but in any case, this is just a stupid thing that I said. But Cosima could collect the particles and analyze the composition of these particles. Also the organic component. But then, of course, it's different to perform measurements in situ and in the lab, as we said, because if we could bring the laboratory instruments up there, then of course it would be different. But at the end, when you put all together, it's easy to make a frame. Okay, this is just to show you the effect of these two bodies put together. This is here. You have what we call the neck of the comet, where it was present also a big fracture, and in fact some models have been drawn to conceive to understand why the body has this bilobate shape. So the idea is that probably two bodies arrived together close enough, but let's say smoothly, and they form this bilobate body. But this, of course, it's a model. It's something that just hypothesis, and it's not my subject, so I will not go in depth on this. And so this is since the shape was quite strange when we first arrived at the comet and we first saw it. Here is the Churyumov-Gerasimenko. But then you have also other comets, other minor bodies that can somehow resemble to this bilobate morphology. Changing in morphology have been observed because we were passing on the same surface many times. So, for instance, here you see that everything is smooth, while here it's somehow some ejection or something occurred here, and also here and here. So, studies have been done also on the changing of the surface, maybe also some modification in some of the structure present on the nucleus. Then, as I said, eyes on the surface, even if with Rosetta, what the data suggest is that even if the comets were normally called dirty snowballs, like suggesting the idea they are made half and half between volatile and dust. In fact, from Rosetta data, it seems that the volatile component is much the ice component is much less than dust. So they are not so rich in water ice, and this is also together with the measurements performed by Rosina on the deuterium and hydrogen ratio, which is quite different from what it's this ratio on in the water, in the terrestrial water. It seems that this theory that it's seeing minor bodies bringing water on Earth, it's a bit discussed. Not disgusting, but discussed. And actually, there is still the theory that asteroids are more rich in water, but let's say that something remains for you to study. So this is the good news. Okay, dust and gas. Of course, the comet, it was then active. We measured a lot of for JADA, it was very happy situation because we were collecting dust and trying to characterize the dust flux in the dust coma. In some occasions, there were these called outbursts, which was an activity, let's say, out of the average of the activity. Different measurements were performed by both by dust instruments. There were 3 dust instruments, JADA, COSIMA, and also MIDAS, and by gas instruments, Rosina, but also Osiris observed that these events are a bit peculiar. So the activity seems to rise suddenly and then go back again. But still not clear which is the process, as I said, of cometary activity and outburst activities. This is, I like very much, these are images put together by Osiris, and you see that there is also on comet, there is rain, but it's a very different rain because this is dust actually. So it's the dust particle that is ejected for cometary activity, but some of the particles would go back on the surface again if they do not have the speed, the trajectory adapt to leave the body, then they would come back, and they formed some deposit of dust that was observed. They were observed on the surface of the comet. Okay, this is just the lander descent. As I said, it was ballistic, so no thruster to control the motion. So it was, it was a very difficult aim to be reached. Not all did believe that it would have been a success. Maybe nobody, but at the end it did. Unfortunately, and this is the only thing that didn't work in the whole mission, when the lander arrived on this nice and smooth surface that was actually selected and foreseen, and so it was a success also in that case. 2 things, the 2 apparatus that were supposed to make the lander staying on the body, which were 3 harpoons on the legs of the lander and thrusters that were fired to let the lander being kind of fixed on the surface. They didn't work. So the result was that the lander arrived and then jump and then arrive again and then jump, and then at the end it was lost. It was lost, but this was not very nice because there was an instrument that needed data both from in situ and from the orbit, and especially let's say that the data from the instrument arrived for the first phase. That was the phase designed to be acquiring data with the battery of the lander. But after that, you saw that the lander was covered by solar panel. The landing point was chosen also because it was exposed to the sun, so that the battery could have been recharged. But actually, since the final landing place was not the right one, the only acquirement of data was those that were performed with batteries. And then also the position was very, as I said, very important to know because of the interpretation of data of the instrument that was both on the spacecraft and on the nucleus. But it was very difficult to find this lander till the very end of the mission. Everybody was looking for actually the Osiris team mainly, and also from ESA, somebody was checking the images to find the lander, the position, the final position. But till the end of the mission, that was in 2016, September 2016, you see that the rendezvous with the comet was in 2014, so 2 years of measurements around this comet. You can imagine how much data are there. And and at the very end of the mission, the first days of September, the Osiris team, looking at these images, finally could find the lander. You see here this very small spot here. It was identified as the lander. The lander unfortunately landed with legs a bit up, not upside down, but obliquely. So this meant that the driller that was supposed to take the samples and distribute it to the instrument that were mounted on the lander, unfortunately was more a fan than a driller. It couldn't work because of the position, but in any case, also the instrument on the lander acquired and transmitted the data. So this is the end of the story. This is a cartoon. I think it's a very nice cartoon for children, but because it's very serious in what it's saying. So on comet and science, it's very. And I have to say that with Rosetta, it was very special. Also, the outreach that normally is very special for NASA and less for ESA, but for ESA, for Rosetta, it worked really well. So it was really, and also these devoted to children in such a serious manner. I think it was very well done, and. Yes, as I wrote here, the technological enterprise for sure ended, but there are a lot of data still to be analyzed and understood. So for young people, it's plenty to be done. Then perhaps a future cometary mission will go back again on Rosetta, and this is what it will see. Rubbish again, also on the comet, but as we said, science has to go on. So sometimes it's even against our principle. Okay, so I have time to rapidly go through this next step, which is the Comet Interceptor mission. You see here that in this sketch, this is the Sun, this is Earth, and here this small orbit is the orbit where the comet interceptor spacecraft, that are actually 3, but I will tell you about, it will be orbiting, because at launch, the target of the mission is not known yet. It will not be known till when the spacecraft, this is the plan. Maybe things will be changed, but as planned is that the spacecraft will be orbiting around the L2 point. So waiting from Earth with the very powerful telescope, which is a very new telescope. It's Vera Rubin Observatory in Chile. It's an American telescope with which we collaborate. Some of our team is involved in this project development. So we are working also on the target selection side for the mission, in addition to hardware and instrument development, because from that telescope, which is scanning the sky regularly every night, there will be the possibility to find, but actually the probability is very high. We made some calculation, and the probability to expect more than one dynamically new comet enter in the internal part of the solar system. When it will be discovered and when it will be settled that the orbit, the activity, and everything will be okay for comet interceptor to depart from this stable orbit. So of course, after detection, then the orbit has to be calculated and everything. So when it will be okay, the spacecraft will leave this orbit and will go and intercept the target. So it will be a flyby, so a very fast thing that Rosetta observed the comet for 2 years. This will be measuring, the instrument will be working for half an hour. So you can imagine the difference. But still, since it's a very new type of object, it will be interesting to have this data. But then, of course, you cannot compare the budget you used for Rosetta and the one you have to use here. This is called a fast and cheap, but not said, but also cheap mission. So it will be, it has been built also with instrument that had high TLR, so the readiness of the instrument had to be demonstrated to be quite high. In our case, we flew JADA on Rosetta, so we got that experiment, and we used one of the subsystem of JADA to be developed for this mission. This is the disk, the disk instrument. It's actually not aesthetically beautiful, but it's a box. This is the measurement plates, the impact of the hypervelocity particle arriving on disk. It will produce some waves on the sensing plate, and these waves will be measured by sensors that are in the corner of the plate, and these waves will tell, let's say the signal is connected to the momentum of the particle impacting the plate. So since we know the speed of the particle, which is not really the speed of the particle, because the flyby is so fast that the speed will be the speed of the spacecraft, so it will be very well known. We will derive the mass of single particles, and we will count the particles, and then since the spacecraft is actually made of 3 different spacecraft. You see, this is the main spacecraft, spacecraft A, and then you have another small spacecraft B1, which is developed by the Japanese space agency, and then this other spacecraft, which is B2, it's developed by ESA as well, and our instrument disk is mounted both on spacecraft A and also on spacecraft 2. This will allow us to make multi-point measurements to derive information in a 3D dimension on the distribution of the dust.